Welcome to the ITSPmagazine podcast network. You're listening to a new episode of the Leading Edge Discovery podcast, where host and astronaut Charlie Camarda and his intriguing variety of guests share their visions for transforming the way we work, learn, and solve some of the most daunting challenges on Earth and throughout the solar system. Knowledge is power, now more than ever.
All right. Hello, my name is Charlie Camarda. I was an astronaut on Space Shuttle Discovery, the return to flight mission STS-114, right after the Columbia accident. I will be your host today for the Leading Edge Discovery podcast series, where we will be meeting with experts from the United States and some from around the world, talking about the importance of science, technology, engineering, math, especially research. We're going to focus on research. This first season of episodes is going to be devoted to the aerospace industry, NASA, in particular, how we use complex engineering solutions to solve critical problems. Problem we're going to be addressing initially is going to be the Columbia accident, what caused it, and how do we develop technology to make sure astronauts could fly safe in space. This is particularly something I'm passionate about. I flew on the first space shuttle mission after the Columbia accident, and I relied on friends like our current guest, Steve Scotti, who's a dear friend and colleague, to help us fly safe. Steve worked at NASA Langley Research Center. He was a physicist, a research engineer, specializing in thermal structures, right? Thermal protection systems, also structural optimization. And Steve has some amazing accomplishments that he's going to talk to us about. His expertise is as broad as it is deep, and I'm very proud to count him as a friend of Charlie, a dear friend of Charlie, an FOC. And so, Steve, I'd like to hand the ball over to you. I'd like to thank you for joining us today. Tell us a little bit about yourself and what got you excited about working in science, engineering, and in particular space.
Okay, thanks, Charlie. Hello, everyone. I guess I could start in the early years. I grew up in New Jersey, probably not too far from where Charlie grew up. In fact, we probably had a lot of the similar experiences, same TV station, same sports teams, and so on, are all in the same local area. My family were butchers, and my father was a produce man. He basically delivered produce to restaurants and grocery stores, supermarkets, things like that. Had his own business, which means he worked 24/7. So he never had a day off. So that was not a career I wanted to go into, talking about careers. Also, I was always early on interested in technical things. My father, as much as I loved him, he couldn't handle the screwdriver. So whenever something broke, I had two uncles that always came over and fixed things around the house that were, needed to be fixed, whether it's plumbing or lights or, something electrical. Something that needs, just had some mechanical things fell apart, a shelf fell down. So I always hung around those uncles. When they came over, I was amazed what they could do. And I think that kind of got me started thinking about technical areas. Also, my early years was the start of the space program. Really, I still can remember the first launching of the Alan Shepard in the first Mercury capsule, first human in a Mercury capsule. And I remember seeing that when I was, 5 years old, something like that. I was pretty young. And then of course space was all the rage back then. So that those two things kind of went together. And I always had a desire to work for NASA after that. I think, I wanted to be a technical person working for NASA. I really didn't want to become an astronaut as much as Charlie did, I don't think, but I think I wouldn't mind doing that either, but it's hard to do it all. Charlie was able to do it all. I could not do it all, but
Hey, Steve, I want to stop you. It's very interesting because I didn't realize we were this similar. I knew we were very similar, Italian American grandparents' roots. immigrants. I didn't realize your father was a butcher, but knowing that he worked 24/7 like my father, who was also a butcher, I don't know if your mother's influence, but my mother was always telling me, you see this, you don't want to work as hard as your father, right? You don't want to do that kind of work.
Yeah, my mother, she never, that was not something she would say to us, but she did complain when, all of a sudden that during a meal, my father had to go, deal with a customer that called because our phone was always ringing. In fact, my father had the fastest finger dialing a push button phone of anyone I ever saw. He could get through a number in probably a second and a half. He could punch it so quickly and not make many mistakes. So anyway, but yeah, in some ways, very similar that way. I didn't realize, your father was 24/7.
My father was also not a handyman, couldn't fix anything. And I had uncles, one of them, a couple of them used to work for Grumman. And so this was where, my interest was, which is similar to you, fixing things, right?
Yeah. In fact, I still have a love for, something breaks, before I find anyone else to do it, I want to see if I can do it myself. That's my desire, because I have that, that kind of stuff never leaves you, I don't think. I think you have that from once that bug bites you, you've always got that bug. You always want to fix the problem. And that's kind of what engineers do too. They want to fix the problem. They want a solution. So,
but you didn't choose engineering to start with, I believe, right, Steve? You chose physics, right?
Right. Yeah, that's a different story. Actually, I was going to be a physicist going into college. I really loved physics. I was always amazed by relativity and things like that. But I was also interested in getting married. And I think my junior year, no, it must have been my sophomore year in college, I found out there was basically people that majored in physics were having trouble getting jobs. So a lot of trouble getting jobs, where engineers were in huge demand. So they were close enough. I decided, well, let me change majors, because I was interested in getting married at the time too. I had a girlfriend, and we didn't get married for a few years later, but I wanted to make sure I had a job too. So that was part of it. So it's basically mixing the practical with the technical. Was part of the reason for switching from physics into engineering. So anyway, that's that story.
So I know you started out in industry. I think you were working for McDonnell Douglas, right, when you first started?
That's correct. Yeah, but they were all over the place back then before they were bought by Boeing. But this was in Southern California, so I was kind of a research scientist there. I've got a dog here trying to crawl on me. Sorry about that. But yeah, so I worked for 3 years for Donald Douglas before I came east to work as a contractor for NASA, and then eventually a NASA employee. But yeah, I had a lot of fun experiences working in Southern California for McDonnell Douglas. So yeah, but again, as an engineer, it kind of mixed a little bit of both, because I actually worked in essentially essentially I worked in space science. So basically things like, how do satellites get charged, and sometimes charging of satellites moving through the ionosphere would actually blow out components. And so there was some problems that I helped on. I was just a junior person then. So I just kind of, I did the math and did some of the programming and things like that, but I wasn't as independent as much later when working for NASA and as a research engineer, which I think that's a real part of being a research engineer, is you have to have a bit of independence to be able to follow problems wherever they lead.
And so this was in your DNA. This is something you wanted to do. You love solving problems, research. You got the research bug when you were at McDonnell Douglas. You come to work as a contractor for NASA. Walk us through who were some of your early mentors and how did they fuel that growth in research, that mentorship?
That's a really good question. Thank you. I think when I first started working as a contractor for NASA, I actually had I was lucky. I had a NASA person who was kind of my mentor. I think he was my mentor. His name was Bob Jackson, and he was a tremendously creative person. He would come up with a new idea every day, and lots of times he came with so many ideas. A lot of the people that worked for him basically tried to prove out whether his ideas were good or not. And so I was one of the people that did that for him. And he gave you a lot of freedom, even though I was a contractor. He said, I think he had a saying, as long as you're not studying the sex life of a tsetse fly, go ahead and give it a try. That was an expression he used. And he was right, because I learned a ton of stuff from that. I learned, he also tied me in with a lot of people that were in his network. So I learned a lot of technical areas that were kind of ancillary to my expertise in structures. And so having a mentor like that encouraged you to branch out is really, I think, was critical in my career anyway, because rather than saying, why are you wasting your time looking at this or that, he actually encouraged me to broaden my expertise, follow a trail wherever it led, and really, I think he had probably the most impact on my career of my mentors. I had other mentors who were really good too, that were excellent as well. Jim Starnes, who you're very familiar with too, Charlie, was another great mentor of mine. And to be honest, working for NASA, there was not a person that you go to in another area of another discipline that maybe wasn't your discipline that wouldn't help you if you went and asked them. And that was one of the key things of working at NASA and the NASA Research Center is people had the time for you, and they actually helped you learn areas that it wasn't their responsibility, it wasn't their job description, but they were just willing to help someone who was eager to learn. And that was something I thought was, again, a unique thing at NASA, and I think it's still true today, although it was really true to a very large degree back when I started my career.
Yeah, walk us through a little bit of what the environment was like. You as a researcher now working at NASA and at a research center, NASA Langley Research Center. Tell us about what the environment was like in order for you to nurture you in this growth, if you will.
Well, so the environment then was I can tell you from a little bit of experience, much different than it is today. Everything today is more program driven, milestones, reaching milestones and so on. There was at that time, more like finding a solution or finding a new path to follow, whether it's a new approach for a structure for a vehicle. But you had a lot of freedom to, again, follow these paths to where they would lead. You had the time to do the background research. So lots of times engineers, I've seen this even with youngsters today, they reinvent the wheel because they don't know what's already been done. So we were encouraged really to not just research in our technical area, but also research and literature reviews, going to the library, looking at old reports that from both NASA and outside of NASA, journals, technical articles. We actually were encouraged to spend our time learning the broad breadth of discipline, looking what's been done before. And that's encouraged a lot when let's say you're working for a Ph.D. You have to do your literature review. You have to that's a big part of your actual dissertation is a literature review showing you've looked around the field and aren't ignoring things that have already been done.
And that what you're thinking about doing, the novelty that you're adding to that is going to increase that body of knowledge, right?
Exactly, yeah. But again, if you spend a lot of time doing something that's already been done, you've wasted a lot of time where you could just read an article that said, oh, this is how you do this problem or how this idea works. And so having the time to find out what's been done already was really encouraged a lot then. And that's something I think just because things are more driven by programmatics and milestones today, does not happen as much as it should. And so I think that's something a mentor really, my mentors encourage that very much so. And I think that's something when I mentor young engineers, I do the same thing. Find out what's been done.
And that really gives a good reason for having a rich research culture and environment. I call it was psychologically safe. We could make mistakes as long as we were learning from those mistakes. We weren't making the same mistakes. That's really the definition of research. As we're trying to construct knowledge of something we're trying to understand that we don't really have all the answers to. And you got to work on, I talk about your breadth. And Steve, you were one of the people that when you were in my branch and when I first got to know you, we were just working in maybe different branches. You had this tremendous breadth of understanding. You could pick up a new field and dive into it and learn it very quickly. And so we've had other people on the show that were down and in a particular field, like a Peter Naffo, down and in aerothermal dynamics, like a Mike Nemeth, down and in nonlinear thin wall structural behavior. But you had more of this breadth. And so tell us a little bit about the branch that you worked in and then eventually started leading, and what was some of the technologies that you worked on?
Okay, well, a lot of my area of expertise is in structures, but in high temperature structures. So to understand high temperature structures and how they work, you have to understand how they get to high temperatures. So one of the things that I was encouraged to learn about that was kind of outside the core structures area was atmospheric, aerothermal heating. Essentially, when you fly at a high speed, and either an aircraft or a vehicle enters the atmosphere from space, it gets really hot. And so, how do you figure out how hot it gets? So you have to. So one of the things I learned from some of the experts at NASA Langley was the basics of aerothermal heating. And not just the basis of it, but also how to solve problems in it. So I learned some of the tools you use, understand the basis of those tools, but also be able to use those tools myself to solve problems. And that was one of the things that I was encouraged to do, because it kind of helped the team the branch I was in, especially early in my career, they needed to be able to get those problems solved. And so having someone inside the organization who knew enough to be able to develop the data needed for solving the structures problems was needed. So the heating is the first step. The next step is that heating actually makes things hot, and then how did that temperature on the outside get to the inside? So you had heat transfer, and how different as a heat transfer. So actually, heat transfer is something I knew fairly well before I came to NASA, because that was one of the areas I really studied. But again, a lot of structures people don't delve into heat transfer that much either. So, but I was encouraged to do that, and so I helped develop some tools that we used in-house to do that, as well as using commercial tools and other research tools. So really, it's very much problem. Everything in research, in my experience, has been problem-driven. You're trying to solve a problem, a very general problem, not a very specific problem. Whereas a Mike Nemeth or Peter Naffo was trying to solve a very specific problem. We're trying to solve a very general problem in terms of what's a new structural way that a vehicle can be built that can handle high temperatures and re-enter the atmosphere or fly at high temperatures. So these general problems required inputs from a lot of different disciplines. And I didn't work all the disciplines, but I worked enough that we could make progress. And then I also learned who to go to that was not in our organization. So you could essentially they would be helpful. Sometimes they'd actually solve the problem for you. Sometimes they'd tell you how to solve the problem.
That's a key point, Steve, and you're instrumental. You were a key figure in being able to do this. These are skills that we learned, I think, working in that thermal structures branch, because these would typically not just a component of a structure. This was a system. We were looking at thermal protection systems, thermal management systems as a system at that research level. And so we had people in the branch. You had people in your branch. Steve took over my branch after I left to be an astronaut. And they had this understanding of this multidisciplinary understanding of the physics of this problem. But we also knew if we were getting into trouble or needed to understand something, we didn't quite understand it enough depth, that we had just the right person at Langley we could go to. And so, Steve, you solved some tremendous problems. And when I guess we could segue into the Columbia accident. When I was in Russia and the Columbia accident happened, you were one of the first people I called up, because we had to start assembling these teams, this network of teams, to try to figure these problems out. And Steve, walk us through a couple of, and you have many, right? But walk us through a couple of the teams that you helped work on, and what was some of the challenges that you had to solve? How did you go about building these teams? And why did those people on the team working together on these, what I call epic challenges, why was that so critical? Why were you so successful, right, when other people were struggling?
Um, well, and again, my experience is going to be kind of unique because there are many people who worked on the investigation for Columbia, as well as what it takes to return the fly, and for the mission you went on. But the so
Let
so
me
I was
give let
on.
me give a typical example. Let me give a typical example. One of the first things people said was we didn't know if the foam hit the tiles or the wing leading edge. So I said, Steve, if the foam hits the tiles, I call them up from Johnson Space, and I said, Steve, if the foam hits the tiles, what's the likelihood that other tiles could pop off right behind the tile, that empty cavity we call tile zippering, right? I think that was something you immediately jumped in on.
Yeah, and so I vaguely remember that, Charlie, and it turns out that back when the shuttle was being developed, there were a lot of wind tunnel tests done on the shuttle tiles at Langley and elsewhere too. And so luckily there were still some people around that had worked on that because the shuttle had been in service for decades by then. But there were still enough people around and that either had worked on that problem or knew about new people who worked on that problem, and they pointed me toward reports, essentially again doing the research, finding out what's been done in that area. And it turned out that there had been some work done in our wind tunnels, looking at tile out effects. And at the time, I'm trying to remember this because it's been a while since I looked at that, but I think the feeling was that the tests were over tests. They were too severe. So any progressive damage that was caused in those tests would not be realistically found in flight, because the wind tunnels, you can only simulate certain conditions, not all conditions in flight. So they choose pieces of the trajectory and try to simulate that in a wind tunnel. And so, they can get the very early part, they can get the very late part. A lot of stuff in the middle, they really can't do all the conditions that are similar to flight. So what they did simulate that showed any kind of potential damage to tiles that would progress was believed to be an overtest. So they didn't feel it was a showstopper when the shuttle was being developed.
Right. And I remember actually calling those people up the minute the accident happened, people like Ron Hunt, Herman Bohan from Russia. I probably woke them up and I was asking them to collect all that data. But you're absolutely right. So they ran these tests in the 8-foot high temperature tunnel. The tests were more severe. But like good researchers, we would like to run those tests and be able to develop the analytical techniques to predict what happens in those conditions and then hopefully apply them to the real conditions.
Yeah. And of course, back when shuttles developed the capability to do that, to be able to do a wind tunnel test and have an analytical tool like a computer program to actually simulate that was non-existent. And we didn't have the computer power to do that. We actually started getting that power at the level necessary about the time of the Columbia accident, maybe a little before then. And Peter Naufo, who you've spoken with, I know also, he was instrumental in developing some of the best tools for that. But back when shuttle was developed, there's no way to go from wind tunnel to flight.
Yeah.
And now it's a lot more. I think there's a lot more tools available that actually do that and do it well. So there's a lot of engineering judgment in the early days of shuttle that, decisions were made based on essentially the best opinion of the best experts we had, because we couldn't simulate everything. And so that's something where we can do better now, but then there's a tendency to overanalyze things. So you've got to avoid that too. You got to make a decision sometime.
There are a couple other examples of phenomenal teams that I dragged you in. I didn't really have to drag you. Once I put a good problem out there, the people that worked in the thermal structures branch for me and Steve, all you had to do was give them that little hook and they just jumped in. And I can remember we were working the repair effort. And me and Don Pettit, another good fellow astronaut, we were working in his garage. And I said, we're done working in the garage. We have some really good ideas. Now's the time to go reach out to my good friends at Langley let's have a workshop, a 3-day workshop. Let's bring all these other people in there and let's start coming up with innovative ideas. I'm going to hand it off to you, Stephen. You take it away, because you eventually led that repair effort for the wing leading edges.
Yeah. Okay. Thanks, Charlie. Yeah. So, I mean, there was actually several repair efforts, and I was some run by a program at Johnson Space Center, and I was involved in that. But also, thanks to Charlie, they gave us a little rope to be able to kind of do some independent, more advanced R&D. They called it, essentially, beyond just turn the crank engineering, to look at really innovative solutions. And so this was a team that Charlie helped me form, because he was instrumental in actually getting us an ability to do this from the people at Johnson, because you still have to pay people to do stuff. So if they don't agree that it's a good thing to do, it's hard to get a team together.
And so tell us, and I'm going to brag a little bit about you, Steve, because your team was very successful. The teams that we had up and running were struggling. And I was watching them struggle. And that's when I realized that, hey, we could do this. I mean, this was something that we did for 22 years when I was at Langley. Steve, I know the rest of the folks in our branch, this was right up our alley. I said, we could do this problem. So my boss, Kent Rominger, the head of the astronaut office, said, Charlie, okay, we'll go over to the program office and we'll tell them this is what you want to do. And so he gave me the green light. I hand it off to you. Talk about how you put this team together, how you got them to work together, because I think this is important. I think building this network, this research network of teams with the right people, you can get solutions very quickly, and you did. So go ahead, Steve.
Okay, so you mentioned a workshop. So we had a workshop where it was like you mentioned earlier, you want to have people with multiple disciplines, multiple backgrounds there to contribute. And you also want it to be safe. So you mentioned, essentially you want to be able to make suggestions and not feel like someone's going to jump down your throat, because that's a stupid suggestion. We're not going to do that. So the team we put together, one of the things I discovered many years ago is don't say no immediately. Let things develop as far as you can, and before you pull the plug on them, because sometimes it only takes getting over a little bit of hill, and all of a sudden you've got a beautiful glide slope to get down to. So trying to keep multiple efforts, because we didn't know the answer, we didn't know the best answers. So we had multiple concepts and different. We ended up categorizing them to things, or essentially repairs that using change of phase, repairs that use some kind of patch, repairs that weren't even a repair. That basically was just a different way of maybe flying the vehicle. That could, if you had damage, you wouldn't have to repair it necessarily. So we actually had a lot of concepts out there, and we had this tremendous workshop where all these people came together and basically brought their ideas, and we tried to categorize them. We tried to find the pros and cons of each one as a team and individually, and we couldn't get everything done in 3 days, so we actually did it remotely after that. Essentially everyone was able to comment and give feedback on everyone's ideas and what they saw as the good things about it, what they saw as the bad things about it.
And you want to know something? I remember when we were forming those teams, we were picking people based on their capabilities, their expertise, their creativity. So we hired some people from Laura. We brought in one person from Laura Bailey's team at JSC that had some other ideas for tiles. There was another gentleman from Thiokol that we wanted to have, but
I remember. Mm-hmm.
What was his name?
Dean
Lester from Morton Thiokol. We wanted to have him, and unfortunately, the program manager at JSC wouldn't let him be there. But we had enough mix of creative people, technical people down and in, systems people. We had astronauts that could address the operations of it, and they just had 3 days of fun coming up with crazy ideas.
Yeah,
and then you had to do something with it. Yeah.
Yeah, we actually had a little bit. The first part of it actually was education. So we had people talk about the disciplines that are important. So we had an expert in aerodynamics talk about aerodynamics. We had an EV astronaut, like mentioned, Don Pettit.
Don
Essentially,
Pettit.
what are the constraints? What are the important things to know? Because sometimes you can come up with an idea, sounds like a really great idea, except for it's got a showstopper in an area, another discipline.
And luckily we had Pete Naffo there, and we asked him to, well, what are the key parameters that we could vary to make sure this patch doesn't burn up? He did the analysis. In the other session with Pete, we talk about the Spartacus email trail that led to. But with that one expert and that 1 day's of analysis, Pete was able to give us the answers that we needed to be successful, and your team to be successful.
Yeah, I think it's really important to have multiple disciplines looking at these problems. I mean, companies when they're developing a new product do that all the time, but they do it in a very structured approach. We had to do it a little more of a freewheeling approach for several reasons. One, we didn't have a huge, budget or organization to do it, and we also had a kind of an implicit time constraint because we always wanted to fly soon. Soon was a number that kept changing, kept moving downstream. So we ended up trying not to essentially throw things away because it would make the schedule. Because it turned out the schedule was never going to be the schedule as claimed, never turned out to be the schedule. They always postpone things later. So until we were actually forced to, we tried to keep the different paths, the different discipline ideas or ideas that were driven by different disciplines, keep them moving forward and talking to each other, cross fertilization, because to a lot of ways the schedule was artificial. It didn't really exist because it was just a number someone put down and as a target, and no one really knew what it would be.
Absolutely, and I don't know if you remember this, Steve, but I was an astronaut at the time. I don't think I had been selected to be on the next crew, but what was amazing to me was the program office did not consider that repair kit as something that was necessary for flying. In my mind, I definitely wanted to have it. That's why I put you as the leader of this team to make sure we had something in time for the first flight. But what was amazing to me was that the Space Shuttle program did not consider a repair methodology for tiles and wing leading edges as something that was necessary to fly.
Yeah, well, they did support having them, but it wasn't right. As far as I know, again, I wasn't on the inside. It wasn't. We're not going to go until we have those.
No, it definitely wasn't.
But I think it was a mix. There are some people who were much in favor of that, and they wanted at least some capability. So I think it was a mixed bag there. I don't know if there was which party or which camp carried the most weight, but I know there were people who said we just need to fly. We don't need to worry about having a repair capability. So I think there was people who thought the other way around too, and luckily we had some good supporters that supported, especially this R&D effort, developing kind of the ability to repair a very large hull, which is with Steve Polis, who was the orbiter program manager. He was a tremendous supporter for that. And he's the one that kind of kept us going, regardless of the schedule. Oops. Oh, I can't hear you, Charlie.
Yeah, I have some of those concepts for the viewers that are actually on the video, or what they look like, these repair techniques, these patches, these very small pieces of carbon. But Steve, what was amazing was, we did that large impact test, and what we learned from that large impact test was that piece of foam that hit the wing leading edge, we could have a 14-inch by 14-inch pizza box size hole in the wing. And what was amazing was you and your team came up with a way that we could potentially repair even that extremely large hole in a wing leading edge. And no one thought that would have been possible.
Yeah, that's true. And one thing about the shuttle leading edge that a lot of people don't realize is it's a very complex structure, and it's a mixture of carbon, like carbon you mentioned, but there's also a coating on it that's silicon carbide. Silicon carbide is the same material a lot of sandpaper is made out of. It's really, really hard. And so I think for months there were groups of people trying to figure out how do we have to attach to it. How do we actually break through that coating? And one of the persons on our team, who is a tremendous technician, he actually was a tool maker before he came to work for NASA, Ron Penner, developed a stepped drill that basically could drill through the carbon, and not only drill through it, but tap the carbon so you could actually put a threaded fastener into it to hold or repair down, which ended up being something that was adopted by the mainstream program too, because they needed that capability as well. But again, someone like that who has the expertise to be able to do that and develop essentially, you've seen step drills. This is a step drill that also tapped the hole at the same time that an EVA astronaut could use. So it's not just the thing you could get at Home Depot or any other store. This is something that he developed and actually had machined, and was in time for Charlie's flight. In fact, the return to flight, we had actually his drills he developed flew with the repair kit that did fly in that mission.
Yeah, and I have that in my office here too. And that was something that me and Don started looking at very intently, because everyone said it was impossible to do, because like Steve said, the silicon carbide, you make cutting tools out of silicon carbide. You make drill bits out of silicon carbide. So they weren't having any luck until we happened to grab one of Don's spring-loaded center punches, and we tapped the coating with it, chipped it. And once you chipped the coating, it was real easy to drill through it. And so by luck, serendipity, we found that, yeah, we could do this. But more importantly, it was that relationship that we had as researchers at Langley with our technician staff. These amazing people, these model builders that were critical during the early NACA days. And Ron Penner was just amazing. And I remember talking to him after he received several awards for what he did. And we kind of ruined him for life, because he had so much fun working on this amazing challenge and using his creativity, that everything else he was doing at Langley seemed boring compared to what he did.
That's true. Yeah, and you talk about teams. I think one of the things that helps a team really become a high-performing team is that you're given a challenge that really excites them, that they feel is important, that it's so important that basically they go to sleep thinking about it. They wake up, if they have an idea, they wake up excited to be able to go into work to try to, see if their idea can help. So having these problems that are very challenging, and again, engineers love to solve problems. Researchers love to investigate areas that have challenges like that too. And having a challenge that is so critical, like the honorable repair for the Space Shuttle, was a challenge like that. And again, it was a challenge that was so important, that people would really, they by themselves would put a lot of extra time into it. They won't just be a 9-to-5 job. In their minds, they're so excited about it, it becomes their hobby too. They do it outside of work.
And that's critical, right, Steve? And that's why Steve and I, and we'll talk about it in a little bit, about our passion for education right now. I work in the EPIC Challenge program, the EPIC Education Foundation, and we're going to talk a little bit about Steve's work in education for Brilliant Star Magazine. He's director of STEM for Brilliant Star Magazine, and the importance of exciting these kids to go into these challenging areas, these very difficult areas. It takes a lot of study, a lot of rigor, but the hook that grabbed Steve, which is very similar to me, is the challenge. And so that's why I call our program the Epic Challenge Program. And how do you hype that challenge? How do you make it more epic, if you will, in order to really grab just the right people you need that love to solve challenges, right?
Yeah,
you see this with kids. You do a lot of work with kids and students.
Yeah, and that by itself is a challenge, because everyone's different. So what will excite one kid or one group of engineers may not excite others. but I do think if you have a challenge, like you say, a challenge that you'll call an epic challenge, that's something that excite almost everyone that has ability to contribute to it.
And these challenges that we're talking about, they're broad enough in many different areas that you can pull kids even from non-technical areas, and they can be a part of it. And just working on this team is exciting.
Yeah, well, that's true. I think the diversity in abilities, diversity in interests, you always get a better solution when you look very broadly at what's out there.
Steve, this reminds me, because when you were working on this problem, right, you were pulling in these key experts in carbon from NASA Langley that have worked in carbon for 30, almost 40 plus years, have been doing it day in, day out, down and in these material scientists. And you saw something amazing with one of the people that was on your team, because he was able to be part of this challenge, right? He was.
Yeah. Well, I think like the epicness, the word you use, being epic, it being so important, it does energize people. So people that have not had, much enthusiasm, because it's, no one really, carbon was a very arcane area. There wasn't a lot of things being done with it at the time. So all of a sudden it becomes really important. So, and here there are people who could contribute to that, to this epic challenge, and that excites people. And so, people that weren't producing that much before then, all of a sudden, they're energized. So having a problem that really captures your imagination, builds enthusiasm, is seen important, and also I think the way you allow the individuals on the team to work is important as well. If you constrain them too much, if you make it too hierarchical, too milestone driven, I'll use that word. Essentially, there's a balance between getting to a solution and doing it in a very structured way. Too much structure is actually bad for creativity, and it's bad for enthusiasm.
Absolutely. So I call it failing smart, fast, small, cheap, early, and often. Mike Nemeth, when we talked with Mike, talked about, having all these requirements on you to write papers, to create slides for program managers to use, taking you away from what you love to do, which is solving problems, and how that causes an impediment to that creativity and that progress.
Yeah, I think the ability to again follow the path where it leads, your technical path, and make mistakes, because not every path will lead to a good answer. Some may be dead ends, but ability to go to that dead end and say, okay, I'm going to double back and go down a different path, and not with no ramifications. Again, you can't spend a whole career doing that. So there's a balance in terms of how much of that you're allowed to do or you're able to do. But if you're trying to solve the problem, you're almost self, what's the right word for it? Govern. Basically, you kind of know, I have to stop here because it's not getting anywhere, and I need to go back and think about it again. So you don't need people telling you that. You kind of govern that yourself, because you want to get the answer. It's not you just want it. You want your answer to be right. You want an answer that will work.
I'm gonna take a little break here. I'm gonna brag about you a little bit, because like I said, you headed up the metals and thermal structures branch. It used to be the thermal structures branch before I dumped it in your lap when I found out I was selected to be an astronaut. And you are absolutely the right person for the job. Your RTF return to flight activities, aerothermal structures working group. You were on the debris assessment team. We talked about your working on the shuttle orbiter repair team. You were also, and I didn't notice, on the independent technical assessment team, right, for the external tank, looking at the foam and what was causing the foam to come off. But let me brag a little bit about you. Received in 2013 the NASA Outstanding Leadership Medal, 2008 Exceptional Engineering Achievement Medal, in 2004 the Exceptional Achievement Medal for developing the the root causes for the Columbia accident, right? And so one of the other things you received a couple of awards for, and Steve has at least 30 awards from NASA, national and international awards, many technical papers. But I want to talk a little bit about another team I pulled you into because I knew I could hook you and get you excited about this. And this was the launch abort team. We were looking at the composite crew vehicle for Artemis right now, the Orion vehicle. Back then it was called the Constellation vehicle when it was a single stick, just solid propulsion rocket that was going to take astronauts to space station. And they were having problems with acoustics, but we didn't get hooked into this problem. We were trying to save weight, mass for the Orion capsule, and also for the launch abort system. And I go to my good buddy Steve, and I said, Steve, I think we could do a better job of this. And I pulled you in, and tell us where that led.
Okay, so actually we're able to pull together first a small team at Langley just to kind of look at the potential for mass savings. And actually, we actually worked on that maybe only 6-8 months at the most. But we showed enough potential there that we got some of the folks in the program office interested in what we're doing. And then we found out from them that this is the program office for the Orion crew capsule. We found out they actually had a worse problem. They actually had a problem with acoustics. So when I say acoustics, basically when you launch a launch vehicle, you have the very loud noises that actually can be powerful enough. The structural acoustics, the shock waves from a rocket launch could essentially destroy a structure. Especially a thin gauge, structure that's not built.
And especially the electronics, right, that were on the vehicle. And what was amazing when we were giving that presentation, when you were giving that presentation to the program office, we thought they were going to be excited about us saving 1,200 pounds of mass to orbit on a vehicle that was overweight and they needed to save weight. Instead, we were shocked when they looked at the shape of our configuration. And they said, wow, this could be something that could solve this other problem that was really something that would have prevented them from even launching. The acoustic loads were so high that we didn't have any test facility to test. And so then you got handed more money, you built a new team, and you went.
So once we found out that the problem they really cared a lot about was one we had never heard of, which was these acoustic loads, especially when you go through transonic, breaking the sound barrier, and as well as the launch vehicle. But the most important was the loads after you've launched, and they had these problems even back during the Apollo days. But so we actually had a team of people who worked for the program, and as well as a group of people who work with our team, go back again, look at the old Apollo data. The problem was that data was so old, and again we've advanced so much since then that that the data was not that helpful. But they had similar problems during the Apollo days, we found out. But everything was built a little beefier back then, so maybe it wasn't a problem, or maybe they didn't know they had a problem and just survived by luck. We don't really know. But the good thing is that we were kind of given again some support to be able to look at this problem. So we had, and this was a problem where we actually broadened from just a lot of people working at Langley and Johnson. We actually had some people at other NASA centers who are essentially interested in working this problem. So we had a really good wind tunnel group at NASA Ames and NASA Glenn who helped us because part of the problem was we have to understand what the loads were. And we discovered very quickly that there was no way. We talked about computer power. Computer power at that time, and probably still today, really can't predict these acoustic loads very well. You have to do it by test. And again, testing in a wind tunnel is not exactly the same as testing at flight, but you can get some good indications there. So we actually had to do a bunch of wind tunnel tests. And we had some good aerodynamicists who were working on the team. And everyone came up with ideas. So we tried to actually combine ways where we could reduce the drag on the vehicle as well, because we found that the drag was so high on the original configurations that you can get more weight to orbit by reducing drag than by essentially making a lighter structure. So we kind of tried to combine the two, and it turned out that based on tests we did in the wind tunnel, and also some computational work done by some members of the team at Langley, we actually came across the root cause of that problem, which no one knew. No one knew the root cause of that problem was essentially an oscillating shock wave that caused all these acoustic loads. And once we could see that in the Schlieren photographs and the wind tunnel tests, and were able to show the issue with that in a computer program that ran the computational fluid dynamics, and saw, hey, I can't even converge here because this thing is moving so fast, my computer can't resolve it. There was an aha moment there. Aha, this is what's causing the problem. And how do you fix that problem? You put a solid boundary there so that you don't have this area where the shocks can bounce around in. And that's kind of what determined the design. And we did some additional wind tunnel tests that with different outer mold line configurations that helped with that acoustic problem, and they worked great. They really reduced the loads down significantly, and we actually had wind tunnel data to show that. And they ended up making the Orion capsule, the abort system. If you look at it, it's like a bicon. It's got a conic very top, and then it's got like an ogive for lowering the drag below that. And so mixing those two together solved the acoustic problem and also reduced the drag on the vehicle, so you get more mass to orbit. So it was kind of a win-win situation. And there were other disciplines too that contributed too. We had guidance control people working on the how do you, if you aborted, would this be able to be stable? Would we be able to control it? Can we get far enough away? And another advantage is the streamlined shape lets you get a certain distance away. That was a minimum requirement. I forget maybe how many miles away an abort has to get before the booster might explode. And the configuration also improved that metric as well. You're able to get further away than the initial design just because of the better aerodynamics.
And the beauty of this was, and this is where I got to give a little bit of credit to the NESC and Ralph Rowe. We convinced Ralph Rowe that, hey, we need to do this. We need some money, but we needed to not be constrained by what the program office wanted us to do. If the program office was directing this program, they would have narrowed the field. You would have not been able to make the discoveries you made. We had to treat it like researchers would. And very efficiently, very effectively, failing smart, fast, small, cheap, early, and often, you were able to do very rapid analyses. You were able to get some very critical wind tunnel results to compare. And so you accelerated this learning process very quickly. And lo and behold, we came up with a patent. You got a patent for it. And if we look at the launch vehicle right now, the launch abort system on the Artemis vehicle, it looks a lot like the concepts that you were proposing. And so it was another, in my mind, a success story. But the real nuts and bolts of this success story is, yeah, we had good people, but getting the right people, putting them together on the right team. And you mentioned stability, right? When you realized you had a stability problem, right away you were able to go and grab a person that understood stability because you knew you needed that on your team, right?
Mm-hmm. And well, again, having a network at a place like Langley, which had all the different disciplines there, I could go to the branch head, who I knew personally, and say, I need someone to be able to solve this problem. And if it was someone they didn't know, perhaps they may just blow you off, or they may, give you someone that really is not a high performer. But it turned out that we had people that were really good at their job, who were high performers, and who got excited about, hey, we've got a problem to solve, and they developed some new tools that could be specialized to solve that particular problem.
You made new discoveries. You added to the body of knowledge in acoustic loads, what causes them, how to predict them. And, you talk about, in a lot of what I write about and talk about on high performing teams, Steve, it comes down to the leader. And let me tell you something, buddy. I talk about the Friends of Charlie network, but you have the Friends of Steve network, and they know Steve Scotti. They know if he's coming to them with a problem and it's a challenge, it's a worthy challenge, and it's a worthy problem to work, number one. Number two, they get to work with somebody like a Steve Scotti on this challenge, and they signed up to work with you more than any other person. I remember Ralph was talking about the people in the NESC were looking at some of these problems, and I don't know where you're going to find the people to work. They were all doing other things, but you found the right people. And I guarantee you, they wanted to work on this problem because of you, Steve, because you were the leader of that team, and they knew how cool it would be and what an exciting problem they got to work on.
Well, I'm not sure that's true, but I'll take
it. It is. The listeners will have to believe me on this one. But Steve, you're amazing. You know that. You're a good friend of mine, and I can't stop bragging about you. But we're going to close out this podcast. We could have 2 or 3 podcasts with you, believe me, and pick your brain. But I want you to be able to give your thoughts, some things you want to leave with the audience about what you think about where we are at NASA right now, your ideas for where we should be going. And then I want you to close by talking about what you're doing right now, your passion with the kids and with education.
Okay, well, I appreciate that, Charlie. I think, what NASA could do or should be doing, I do think one of the things that I've seen in my career before I retired, from my early days to just before I retired a few years ago, is essentially the narrowing of the ability to branch out. So everything being so driven by a program and a milestone that a program manager, doesn't care about, anything but meeting that milestone. And when I started working at NASA, I never even saw a program manager because the research was more driven by the managers of the research branches. So you had someone like Jim Starnes, who was essentially world renowned in structural mechanics. He laid out in his mind how the discipline of structural mechanics, especially in composite structures, needs to advance to be able to be useful to aircraft and spacecraft. In his mind, he laid that out essentially a decade or more worth of work that needed to be done. And he methodically found funding for it and was able to mentor younger engineers to work in the different areas that needed to be worked. Damage tolerance was a big area, fatigue and fracture. Manufacturing became later. Structural concepts and structural response and how that works in both shells, thin shells, and as well as more thicker structure that behaves totally differently. But someone that had that expertise in the discipline, they're trying to position discipline so it can produce practical results. So he wanted to be able to see airplanes flying that were composite. He wanted to see spacecraft flying that were composite.
And you mentioned something that before I forget, that's very important, Steve, is that we had an independent research budget, number one. And also, rather than hog that budget just for structural problems, if he knew that he needed materials expertise like fracture mechanics and damage tolerance, he would give that money to those people because it was a highly coupled interdisciplinary problem. So it wasn't that competition for funding.
Yeah, and so that's true. And so having leadership that had potentially managerial leadership as well as technical expertise, it's still good today, but not nearly as good back as when I started the career, because then the technical managers were also the managers of the people and the programs. So you had, again, world-renowned engineers like and researchers like Jim Starnes, who actually had a lab named after him because he was so proficient in his area and produced so much. It was so well known that he deserved to have something named after him. But having that, someone like a Jim Starnes would have let you branch out a little bit, whereas a program manager today that doesn't have the technical background would not necessarily give you that freedom to do that. So that's one of the things I think has changed, not necessarily for the better, for the worse to a large degree, because some branches off the path that the program says you want to go on could be even more fruitful branches than the ones that they're telling you to go down. So a young engineer has less freedom to be able to pursue these side interests. And of course, you can always do it on your own, but you can only make so much progress on your own. But that's something I think that's not has been a negative perhaps over the years as NASA has evolved. Little less freedom for the researchers and less guidance from the really smart technical discipline experts for the young engineers to be able to be mentored and be able to move into a path that potentially could make their own career into one that's really they become an expert in. So that's
excellent.
one area
Excellent.
to talk about.
Excellent take on that, Steve. So tell us a little about your new passion. You're the STEM director for Brilliant Star magazine. Tell us why Brilliant Star. It's also part of your faith that you got interested in this one organization. But tell us how much fun you're having and what you're doing with young kids, getting them interested in STEM.
Well, actually, Charlie was actually influential in me really getting an interest in STEM education for kids. And it's because of actually a friend of his from Boeing that showed me some data that just shocked me in terms of if you start from kindergarten up through college age.
And that's Mike Ritchie, the chief learning officer at Boeing, another good friend that we're going to have on the podcast.
But he showed data where essentially if you start with 100 people or have 100 kids to start, year by year as they go through school, how many drop out and lose interest in STEM. And a lot of it, and it kind of falls off a cliff by the middle school age of kids. So you're going down and then all of a sudden, there's a big jump in the middle school age. And this was data that he had accumulated as part of his job for Boeing, because he was trying to essentially work about education for the next group of Boeing engineers. So he had to do his own research. And this is one of the research things. And I saw that and I'm thinking, wow, that's an age group that really is important, the middle school age of kids. And it turns out that I'm a Baha'i, and so there's a children's magazine called Brilliant Star and so they have a printed magazine on the website that actually was looking for an editor. And so I was going to retire soon, so I contacted them and said, listen, I'd be happy to volunteer. Once I'm retired, I don't need you to pay me. I can just contribute my time to it. And so I was going to do that as an editor. I said, well, what we really could use is someone who's really good in your background in the STEM field. So they actually create a position, a volunteer position they call it the STEM Education Advisor. But and they've given me again a lot of rope to be able to hang myself. But so I've actually have a column in the magazine almost every month, essentially called Space Ace, where I answer kids' questions, or when I can't answer myself, I go and use my network and I get experts in different areas. And I've talked to several engineers like Charlie and Don Pettit and Leland Melvin, and they've answered questions that kids have, especially if it's an area about being an astronaut. I can't answer them from experience. Charlie and Don Pettit and Leland Melvin can. So if in any discipline that I don't have the answer for, I try not to answer it myself if I can find an expert that can do it. So I'll reach out and increase my network by talking to the experts. So they answer kids' questions on Space Ace. And then I just write articles in different areas where I try to combine values and science and science education, STEM education, where persistence is an important value. And you can't make scientific discoveries unless you're persistent. So I wrote an article on that, and there's actually a scientist that discovered essentially a cloud that follows the moon. That essentially it's actually a false moon that he predicted would be there, and took him years to discover. He finally discovered it. But his persistence was something I brought up in the article, and other things like that. Try to tie the world of values to the world of STEM and show how there's a lot of connectivity there. So I'm doing that both on the website as well as in the magazine, and I've also been able to have.
Steve, can you give us that website if the audience would like to contact and see what you're doing?
Yeah, so the website is brainstarmagazine.org, and Brainstar Magazine is one word, so brainstarmagazine.org. And so I've got a landing page on there, a STEM landing page that has jump off of articles that either I've written or I've wrote people into writing. We also have some videos, Charlie's in some of them, asking questions of astronauts. Leland Melvin mentioned, he's in one. We had some
Don
other.
Pettit.
Don
Pettit's my all-time favorite.
So we've had interviewed some astronauts and put them on video, short videos, like 5 to 10 minutes long, where they're answering kids' questions. And one thing that I did recently that, again, it was kind of fortuitous, the technical director of the magazine, the creative director, asked if I could help. They had a problem with, they had actually an art app that essentially kids could draw with. It was a web app, so on the website you could draw things, and she said, "It's broken, can you fix it?" So I actually spent about 2 years developing a new app that's now live. It's called Imagination Station 2, and so you can get to it and you can draw things. You can bring clip art in. You can save your drawings and go back to them later, and it's a lot of fun to be able to. Again, it gives kids a creativity is a big part in my mind of research engineering and engineering. Scientists just don't do math. They have to be very creative in what they do. So it's some even artistic in some ways. So STEM to me includes things like values, like mentioned, like persistence, and also you need some artistic flair and artistic creativity. So STEM is a very broad field, because basically everything we do, when you think about it, has some STEM app. Either STEM has some involvement in it, or it's
STEM or STEAM, right?
STEM, STEAM.
Yeah, because you have to have the arts in there, Steve. And even old guys like us, for those that are watching the video, you can see the excitement in old guys like us. Even Steve gets excited about it, because it's that creativity, having that fun. And science should be fun. Learning should be fun. And Steve, you're an excellent ambassador for Brilliant Star Magazine. They're lucky to have you. And I want to thank you for agreeing to be a host on this podcast, for people to get to know you a little bit more. And I want to thank you very much, buddy. Thank you.
Thank you, Charlie.
We hope you enjoyed this episode of the Leading Edge Discovery Podcast with Charlie Camarda, part of the ITSPmagazine podcast network. If you learned something new and this conversation made you think, then share this channel and ITSPmagazine.com with your friends, family, and colleagues. If you represent a company and wish to associate your brand with our conversations, sponsor one or more of our podcast channels. We hope you will come back for more stories and follow us on our journey.